Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to start to talk about the Gauss Law, one of the most foundational equations that is normally used throughout the whole electromagnetism study. So before we get started, please consider subscribing as well as liking the video, and also make sure to check on the description below for the notes for this discussion. So let's just get started by actually discussing the electric field lines itself. So last time we have talked about the electric field. And so there are ways for you to draw these electric fields. One of them is by only doing arrows. But another way for you to draw such field lines, to draw such electric fields, is by using the field lines. So let's just state if I have a positive particle, and if I want to draw its electric field, it might have a direction in these directions. So if you actually try to consider what is the meaning of these field lines, the more closely packed it is, the higher or the lower its electric field is, or basically its magnitude. And the direction shows you in which direction does the electric field lies in. This is very similar to the fluid motion, in which we discussed that if you have a much more denser, packed field lines for flowcharts, for flow lines, it means that the flow is faster. This works the same thing in electric fields. And if you actually now start to consider the electric field as well as the flux for a given electric field, we would actually observe some things. So first, let's just discuss about the electric field itself, since I haven't really defined what the flux is. So at the top here we have this particle, and let's just draw some arbitrary shape. This shape has three objects going in. There is three electric fields going in, and three electric fields going out. So if you count the amount of electric field lines that goes through this object, in total it will be 0, since there's 3 in and 3 out. But this is different if you actually include one of the charges, in which you would figure out that there's 8 in and there is 8 out, and none of them is going in. So this gives a certain intuition, is that the number of field lines is proportional to the charge. So if it has much more field lines, that means that inside this surface there would be much more charge. And so only by developing this idea, we can actually think about when it goes continuous. So the easiest way for you to compute these things when it goes continuous is by assuming that it is actually basically the electric field, multiply that by the area. But in here I will just put that into a vector because we want a scalar quantity. So we would have the electric field, multiply that by the area. Well, it's the area with its vector pointing in the normal direction. And if you have this surface to be changing, as if its slope is changing, you could just write this in the term of the integral of the electric field times the dA vector. And this is what we'll call as the phi itself. So what phi is that it basically tells you the electric flux. It's pretty much the electric field multiplied that by the area. So let's actually consider certain types of surface. So in here you need to have a surface as well as the electric field. Let's just state that the electric field is going in this direction, and then you have this plane within a certain direction. The way for you to compute the flux is to actually just to do its dot product with its A here. So it's just E vector dot dA, or A vector, because it is only within one direction. So this would mean that it's E vector times A vector, multiply that by the cosine theta, where the cosine theta is pretty much this angle. Or you could actually just draw it something like this. So that's pretty much the theta itself. So that's how you define the electric flux when the vector is a little bit different. But you have already computed about this on General Physics 1. So we will just try to develop this idea of using this electric flux into solving what is the charge inside this entire surface. And that's pretty much what you call as the Gauss's law. So let's actually think about the point-like charge. So we would have this point-like charge, and let's just put a surface at the outside. So we could actually try to compute what its electric flux is on the surface, which is a closed surface. So I would just create a surface which is something ball-like. So it's pretty much a sphere encapsulating this entire particle. So if you try to compute its electric flux, it would be the integral. No, sorry. So first thing that you would actually notice is that the electric field could be written as kq over r squared. So we could just write that as the k times q over r squared, and then for the dA vector, so if you actually try to look at this, so let's just write this as dA vector first. So this is basically in the r hat direction. So pretty much dA is this small surface here. And if I try to check a different surface, as long as it has the same area as well as the same radius from the center, so pretty much from here to here, we'll call that as r, we would see that it's pretty much kq over r squared, the integral of the r vector dA vector. So this gives a certain intuition first. And also, another thing to discuss is that the dA vector dot the r hat is pretty much the area. So it's pretty much just so pretty much the dA vector itself is basically dA times r hat as well. So r hat times r hat is pretty much 1. So you could just cancel those guys out. So we would only have the dA. And this dA, when you take the integral of dA, you would figure out this area of this entire sphere, which is 4 pi r squared. So we get the relation that it's 4 pi kq. And this might seem hard for you to write. So instead, let's just write this as q over epsilon 0. So what is epsilon 0? So mathematically, epsilon 0 is pretty much epsilon 0 is just a number, which is 1 over 4 pi k. And if you actually compute this, this is about 8.85 times 10 to the power of negative 12 coulomb squared per Newton meter squared. And what does it mean physically? This is just a number which is related later to the dielectric constant. So this is something which you call as the permittivity. But much more specifically, this is the permittivity of a vacuum. And why is that? So if you actually put a material and if you give it an electric field, it might react a little bit to cause a different permittivity. It could go even lower than this permittivity of vacuum. So this is very specific that it is the permittivity of vacuum. So what we observe here is that the integral itself is the Q enclosed over epsilon 0. So it's an interesting feature to discuss. Is that if you know the flux of an entire surface, you could figure out its charge with a certain proportionality constant. So let's actually try to discuss certain ways for you to use the Gauss's law. Let's just first try to discuss about if I have this spherical, not metallic, but it has a uniform charge. So its total charge is Q. And let's just state that I'll just say this guy to be the origin. And I want to create a sphere or like a bubble which will basically expand. And so what I'm doing here is that I'm using a little bit of symmetry so that I can get the electric field at each point. So let's do that. So let's just observe. So if I call this to be R and then this small guy to be the small r, if I actually observe when R is less than R, you would see that this flux should be 0 because it doesn't have any charge. So that brings up something. First, the E vector dot dA vector will be a constant. So anyways, this will be E times 4 pi r squared, which is 0. So that means that the electric field inside of the surface is always 0. It doesn't matter what the case is, inside of it is always 0. What about if it's R equals to R? Well, if we actually go and do the same integral, well, in fact, let's just actually do this greater and equal. So this will be E vector dot dA vector, and this will equal to Q over epsilon 0. So Q is pretty much what is enclosed by this surface. So anyways, this distance from here to here will be very small, very small. So we would get this. So we know from the spherical symmetry that it shouldn't change much for the electric field. So we could just bring it out, and then it's just the integral of the dA vector, which is just the area. So we would obtain that it's the E vector, multiply that by the D, well, it's technically the E, multiply that by the dA, and the dA itself is 4 pi r squared. This will equal to Q. So the E is pretty much, Q epsilon 0. So it's Q over 4 pi r squared epsilon 0. And this is pretty much KQ over r squared. So it seems that if you even have a spherical charge distribution with uniform distribution, it is technically almost similar to the Coulomb's law. And so pretty much the Coulomb's law comes from Gauss's law. But you couldn't get Gauss's law from the Coulomb's law. So it's very specific that you could actually use the Gauss law to compute the electric field, and sometimes it is way much more easier for you to compute the electric field by using Gauss's law. Let's figure out another type of symmetry. Instead of a spherical symmetry, let's figure out line symmetry. So let's just state that I have a wire and it has a charge distribution of lambda. So pretty much this wire goes from infinity all the way to infinity. And I want to figure out what's the electric field at a distance which I will call as r, or maybe x. Maybe I'll just use r. So this is the electric field. So what is its electric field? So we'll just use another type of symmetry, which is radial symmetry. So last time it was pretty much radial symmetry in all different directions. You could just use some form of spherical coordinates, but in here we'll just use some form of polar coordinates. And so if we actually construct this cylinder, so pretty much the way that you actually use Gauss's law is that you just need to define your own surface. So in here I have the cylindrical surface, and so what I know is that on these caps, its dA vector and the E vector is pretty much perpendicular to each other. So we know that the flux in there would be 0. But for the one facing outwards, must to be non-zero. So if we actually write this down, E vector dot dA vector, this would be the E vector dA vector for the caps. And there are two of them because it's pretty much in symmetry. And you could add it with the integral of the E vector dA vector of the shell or the coating or the blanket. So from here we know that this guy is 0 from the way that the vectors are formed. So therefore the Q over epsilon 0, so the Q in here is lambda over L, so I'll introduce this guy to be L. So it's pretty much the length that you choose. It should be lambda L over epsilon 0. So this E vector, the A vector, has to be. So if you actually observe this again, we would know that the E vector and the A vector should be parallel to each other. And because this is infinite, it works for almost every single point. So we can just separate the E vector out because it also has the symmetry as well, and the integral of the dA vector. So we would obtain this to be E times the dA vector, which is basically the area. So the area would be its circumference, which is 2 pi r. Multiply that by the length, which is L. And this is equal to lambda L over epsilon 0. So we would obtain this to be, so we would obtain E to be lambda K over 2 pi r epsilon 0. So this is pretty much, oh sorry, it's lambda L. Yeah, it should be lambda L. Sorry, my bad. So, oh yeah, so the L will cancel. So you could write this down as 2k lambda over epsilon 0 times r. Oh no, sorry, there shouldn't be an epsilon 0. So this is something interesting. We observe here that this dependence is within 1 over r squared. And for this guy, its dependence is within 1 over r. So it seems that the electric field is much more stronger. Compare that to the spherical shell. And we could actually also try to do this, but instead for a line symmetry, we could just do this with plane symmetry. So we'll have a plane like that. And we want to figure out, so we'll just apply a sigma, which is the surface density. And I want to figure out what's the electric field. Assume that this guy goes to infinite anyways. Infinity and infinity. So it might be hard for you to compute this, but if we actually just try to draw, instead we could just draw this into some form of a prism. We will first notice this. The area on the blanket, so the blanket itself, its flux would be 0. But for the surface itself, the surfaces, and there are two of them, one of them in this one and the other is at the back side, it would be pretty much non-zero. It's not 0. So the phi of that. So you can pretty much figure out what the phi is. So it's the integral of E dA vector over the Q enclosed, which is in here. It's sigma times the area. So it will be E vector over epsilon 0. It will be E vector times A vector. So it's pretty much just EA because it's pretty much parallel to each other. So it's EA times sigma A over epsilon 0. So we figured out what the electric field is. It's sigma over epsilon 0. So you could see something else here. This guy has the dependence of 1 over r to 0. And pretty much this is the only thing that you need to know from the symmetry. So if you actually observe the fields of arbitrary charge distributions, you would see that if you have a plane charge, something like this, it would have a dependence of 1 over r to the power 0. And for line distribution, it's 1 over r. For spherical symmetry, it would be 1 over r squared. And if you have a dipole, which we have already done the last video, we figured that out to be 1 over r cubed. So pretty much you could see the difference when it comes to the difference in the radius. So it's important information for you to know. So we have already talked about Gauss's law. So I want to actually try to tell you about conductors itself. So last time I tell you that a conductor pretty much allows charges to move. And if I have this material, anything, and I apply an electric field, pretty much I know that inside a conductor there will be free electrons, which will freely move. So these electrons will move according to the electric field, which means that it wants to go in the opposite direction of the electric field. So there will be charge buildup in one side, while there's some positive charges left behind. Pretty much the holes, if you actually go into material science, specifically semiconductor industry. So observing that on one end, it has this there is this big distribution of negative charges, and the other, it has a big distribution of positive charges. Eventually, there should be a equilibrium in which that the electric field inside would be 0, as you could just create another electric field, when you sum it up with the electric field applied, normally called the H field. So this is the applied. If you actually sum them both up, inside of this conductor, its electric field should be 0. And that's for an ideal conductor itself. So there will be a buildup of charges such that inside of this, there wouldn't be any electric field. It's like as if that it goes like that, the material, and then it goes something like that. It's pretty much like a dipole. But there is some other electric field applied from the outside. So in here, we could just develop the idea of electrostatic equilibrium. Is that if you apply a electric field into a conductor, it will have electrostatic equilibrium when the conductor itself doesn't have any electric field. That's the idea. So what about charged conductors? What happens if I have a conductor itself, and instead of using the electrons that is already available, I just introduce more electrons, or even remove some more electrons? What would happen? Well, same idea. Let's say that inside it's a positive, and there will be some other interactions with other positive charges, so they would likely repel as far as possible. So instead, what happens is that the charge instead dwells in the surface itself. It is not inside of the conductor, but it is within the surface. So So this buildup of charge does create a electric field. And the way for you to compute the electric field is simply only by using the idea from the previous idea, which is sigma over epsilon 0. That's pretty much the electric field. If you go very close from this surface. So this gives you an idea of how do you protect your home from from unwanted charges such as lightning. One way is to actually to shield yourself by using some form of a container from the outside. So if you are inside in here, and if there's charge applied, instead the charge will be in the surface, and if it is hooked to the ground, the charge will instead go to the ground. So that's pretty much the idea, and also it's pretty much how lightning rods even work. If I have a lightning rod and it goes towards the ground, pretty much that the wanted path for the lightning would be at the least path, in which it will go straight towards the ground as soon as possible. And one of the easiest ways for you to do that is to actually to go into a higher place. So if there's lightning striking this lightning rod, instead that there will be a buildup of charge here. And since conductors wants its charge on the surface, it will instead be distributed on the surface. And this will allow it to actually to transfer its charge straight towards the ground as well. But technically the ground itself is not really a conductor or a insulator. It's pretty much a pool of net charge, of neutral charge pretty much. So that's how lightning rods work. And so that's pretty much all about Gauss's law. And so if you want more of these kinds of videos, please consider subscribing as well as liking the video, and also share this video to others so that others could actually learn physics in a much more better way. So thank you very much, and I will see you on the next video.